All right, so it's been a while since we took some notes, so let's take some notes. Okay, it's been mostly tutorials. Make sure you know how to do this, right? Okay, so what I'm going to do for the next week, maybe Tuesday next week too, is do some notes and do some programming. Okay, we're going to kind of review, and I'm going to show you typically another approach of FEM that they actually pretty much use on a daily basis. ANSYS actually uses these. And it involves using the differential equation or a differential equation to solve for values. Okay, so this hopefully you've seen in heat transfer, right? Second derivative of t with respect to x is some function. If the function is equal to 0, then you've done that, you can solve it. Okay, but basically that differential equation can be used on this plate or fin to solve for temperature distributions this way to the x. Okay, this is a distance L, and that is used to solve the temperature profile. Okay. How many boundary conditions do you need? 2, right? Because it's a second order. Okay. So T of 0, when x is 0, could be a temperature. And T at x equal L could also equal a temperature. Does it have to be temperatures, or could they be? There could be one temperature, one derivative. Oh, hold on one second. Oh, did she leave? Oh, okay. And then, or you could have 2 derivatives. Doesn't matter. Okay. All right. Second thing, just to kind of review, if I look at this differential equation. Is it linear or nonlinear?
It's linear.
It's linear. Okay? I'm going to show you this one. This is nonlinear. Because K, oh, I picked the same color. In the linear case, K is a function of X. In the second one, K is a function of T, and it becomes tricky. It's much easier to solve linear ones. What is X? Is X the independent or the dependent variable? What is it? X is the independent. Because T depends on X. Yeah. That means T is the dependent one. Okay? All right. So, up here, we're going to take this bar, and what I'm going to do is I'm going to show you temperature as a function of X. Okay? So we're going to make a graph. T of X, X. And I might as well do it this way. Sure. So whoops. Actually, let's do it this way. 1, 2, 3, 4, 5, 6, and so forth. Okay, and this is going to keep going and going, and I'll talk about that. Okay, I want to grab something real quick. FEM. We are way off schedule, so let's see if I have it here. Okay, maybe I don't have it. Oh, here we go. Should be in here. Nope. That is not the one I want. Okay, that's fine. Okay, so looking at that graph, if you look at the purple circles, 1, 2, 3, 4, 5, and so forth, those are the elements. So what we did is we took this section here, which is a fin or a plate, and we cut it up into many elements. And you've done that with the discrete stuff. And then each one of those dots represents a node. Okay? So what you're doing is we're going to look at this slightly different. Before, you would split up the elements, and then at each element you invert K and solve for those, right? Well, we had equations already developed for each element. This time, what we're going to do is we're going to look at a differential equation. And if you remember this one, and we're going to develop elements for that differential equation. Okay? So instead of having equations already developed for us, like you did with the direct formulation, because it was a direct method, we had equations. This is actually the more appropriate method is you have a differential equation that solves a particular problem, and you're going to split that up. And you're going to look at that for each element. Okay? So what you have to do is inside this differential equation, it's second order, right? And there is approximations that we can do to actually guess that different second order. Okay? What? Do what? We haven't guessed anything. You solved it theoretically, but we haven't done anything else other than that. Okay? And what we can do is we can assume that from here to here, like these elements, or between the nodes, is we can assume it's linear approximation, quadratic, cubic, to the fourth, fifth, whatever, it doesn't matter. Okay? So that's what I'm going to actually start showing you how to do that. Okay? So what we need to do is, I want to show you two things. I don't know why I don't have this on, but let's see if I can actually load this up. let's wait for that to load. While that's loading, where do I want to start with? Let's start with before I show you and dive right deep into what I'm going to show you here, we need to do some programming and understanding how the MATLAB will program. But I want to show you this first. Oops. FEM. Sure, we'll try this one. Oh, okay. I need my computer. That's fine. Let's see if I can do this. Oh, okay. All right, go ahead and grab your computers, and we'll do some programming. I don't have a draft, but I'll find it. I can't use my personal computer. What I was going to do wasn't going to involve that anyway. Okay. So I'll give you a few minutes to load it up. Does everyone have it up? Oh, you already got it up? Oh, you got it all up. Okay. So make a new script. Okay. So what we're going to do is I'm going to show you, before we tackle, okay, we need this linear approximation, we need this blah, blah, blah. There is ways that we can actually guess a solution with cosine and sine that we're going to use to show you first, okay? Then I'll get into that, probably definitely more on Thursday, all right? So what we're going to do is we're going to solve this differential equation. And we'll do it, I don't know if I ever did it analytically. I think I have it. And then what we're going to do is we're going to assume that the solution is this form. So instead of assuming that this differential equation has like a linear approximation, quadratic, you could also assume a sine or a cosine solution. We're going to do this first because it's easier to program and kind of shows you what we need to do. All right. Okay. Go back to your script, and I'll zoom in here. What's that? Okay, so let's start this. All right, A is length of x, tx, x to the fourth, by 12, minus pi third, 12. And make sure you put dots. And let's plot this. So what I want to do in this stuff is help you program, but also show you these methods because they're not easy to do. I didn't give you any units, but that's fine. We can throw those in. So that the T of x is actually, if you did that by hand, theoretical, that's what you would end up getting. Is the analytical solution to that differential equation. Did I give you any boundary conditions? Morning. Doing some programming. You can bring the card over if you want, or just hang out with somebody. It's up to you. Okay. All right, go ahead and run this. Did it work? No. Did you what? Just the script. Oh. There you go. Yeah. Are you looking for? The script. Are you looking for? Oh, right here. No, right here in the script. Right? Yeah. Okay, go ahead and run it. Make sure it works. So, so you got 2. So negative 300. What happens if you take these parentheses out? Around the 12 and the x. Did it change? Yeah. Okay, that's what it's supposed to look like. Yep. And that's what I had in my code. So I modified it. Okay. So use that right there. You get that? Yeah, you get the bell curve. See the space? Yeah, you save it, you gain spaces. And get rid of the parentheses around all the x. Yep. Get rid of the parentheses after the 12 and after the x. The actual temperature. Okay, you got it now? Okay. How you doing, Ryan? Okay, now I won't be able to run it, but because we're going to use Sims, we'll see. Hopefully, everyone has that. If not, we'll figure it out. So now what we're going to do, let me zoom back out, is we're going to assume we've already solved it theoretically, but we're going to use that over there and actually use an times sine of nx and approximate this solution. Okay? So, I will show you how we do that. What? Yeah, you didn't miss anything. I'll just move this. Hold on. I'm going to program it, and then we're going to look at notes. Figure out. Now you can run it, and let me know if you don't have Sims. If you don't have Sims, I think most people should have it. In the wrong place. Okay, let's keep going. And then stop right there. There's a few more lines, but make sure it runs, and I'll go through some of this. Huh? It actually makes the equation in variable form, and I'm going to show you that. But did I put x squared? Yeah, I did. All right, did it actually work for everybody? It didn't work for you. Okay, use manual type ER. Might not have about 2 bars. Why don't we have about 2 bars? About the version, right? Yeah. Should we start down a little bit? Maybe that's why. Sometimes. Like, go to your, can you log in? Okay. That's why. But you should have it, be able to download, because all of these, you wouldn't have all of those. So you should be able to download. I'm not sure how. Manage items. Everyone else at work? No? The graph should go down and back up. Oh, get rid of the on the end of line 25. That's what you do. Oh, it's not working. There's a symbolic. Yeah, right there. Yeah, that's in 7.1. Yeah. How come it didn't show up those versions? Yeah, take ER. It should pop up right there. Try closing Mallet. Oh, this is your. I like the ones where you can pull out the back.
You do have to do something different to press this back.
Just have
What I want is this is not. So,
Hold on. Is it your Cadillac rear end?
Hey, Ryan, how did you get to manage?
Yeah.
That is those are things. Because we're 2016 on 2017, then that's
All right, why don't we go ahead and whatever you need to do. I just want to make sure we get this done.
I should put that
Oh, what is that?
just like a check one or that.
So, I looked at the drive shaft, the axles.
Does that work, Ryan?
No.
It's weird. You might have to contact us. You have it, it's just not installed.
That's fine. That's because mine's 2016 and not 2017.
Yeah.
I'm sure you can see the actual part. Does that have anything to do with it? No.
Oh.
6 feet.
Oh.
And
Yeah,
all
it
more
is.
bodies.
It is coming
Axle. So that it still goes in your hub.
in. Yeah.
It goes in 6 feet.
Okay, just keep writing. So when I just keep writing it, I'll continue that. Worst case
Not
is,
available for data or pre-release or that.
you can log in there after. Okay. So let me just talk about what is happening here. So anytime you do sims, what you do is you make your equation in a variable form. Okay. So where I have that A on line 19, it says int of sine of mx times x squared. That right there, it's basically saying sine of mx times x squared is an actual equation now. Okay, we didn't plug anything in for x. But in order to integrate, which is this int, we have to make x a symbolic. So we're integrating this equation from 0 to pi. Okay? How many times are we doing that? 10 times, because that's what the loop says. Okay? We could change that to 100. Doesn't matter. Okay? Then, if you wanted to see what this value of a was, you actually have to evaluate that a. Okay? Even though we already integrated and it does that, in order to make sure it actually works, that's what you have to do. Then, down here, all I'm doing is I'm just making 2 divided by m, which is 1, 2, 3, all the way to 10. So that's going to be a number already. Okay? So again, symbolic, you can do integration, you can do difference, you can do derivatives, whatever. Okay? You can actually, in MATLAB, solve 2 equations or 3 equations at the same time using sim. Then, down here, what am I doing down here in this for loop? Well, what's g? Lowercase g. What is g? The loop counter?
Oh, right.
Okay.
Okay.
So how many? We're going from 1 to 10.
Yes.
And what are we doing
You're
here?
multiplying the valuation of A,
Of A
times R.
Times r. That's all I'm doing. Okay. All right. So let's keep going. So the next one is n equals 1 to n, and we're going to call this big G. And this is sine of n times x. And then another one, call this E. And some of these you didn't have to put in multiple for loops. I just did it to kind of show you, to break it down a little easier. So what are we doing from lines 28 to 30? All we're doing is we're making sine of n times x, doing that 10 times. We're going to have 10 numbers in that matrix. Then what I did down here in 32 to 34 is I took the an value from line 25 and I'm multiplying it by line 26. And I'm doing that 10 times. And then you can say f come sum of E tx1. Actually, students that can run it, take a semicolon off and run it. On line 36.
Wow.
So line 36, when you say come sum of a matrix, what it does is it adds, like if there's 10 numbers in the matrix, it'll add the first one, then the second number will be 1 and 2. Add it together. The third matrix, the third number in the matrix would be you add 1, 2, 3. Okay? So at the end, the last value of F is if you add everything up in that matrix. Okay? The second to last one is you add all of them but the last one. Okay? So what we need is the last value. And then now we can define what x is. And we can say, hold on, and we can now plot x versus eval of tx1. And let's do squares. It should line right up. Actually, you can put a semicolon on that now. It should line up right with that bell curve. Good work, and I'll show you by hand what all these things are. A little bit of advanced programming. We're doing some integration, we're doing for loops, we're doing evals, something different that you've never seen before. Here's just more practice. The students heard from Cummins to do use MATLAB and Excel. And both companies, Snyder and love FEA or FEM. So everything we're doing in the class, in Inventor. So, or did they both use Inventor? But it's the same thing. As long as you understand the basics, applying boundary conditions, you could. Inventor and ANSYS are pretty much the same. So. Now, did you get it to work? Did it line up with the curve? Did you get squares? Okay. You can. I know you won't be able to get it. It did work, but it won't. Oh, you got it. It's a little slow with the server.
Yeah, that's.
Still not working, okay?
Oh, that's not line 64. That's line 64.
So you were able to download Tim? Or is it about? Oh,
I don't know. It seemed like this is one of these.
what's on the videos?
Like, I need to that part. Can't do this yet. Like the whole version of what the software.
You click on that, you log in, you already logged into your account.
Yeah. I'm probably gonna upgrade to do that.
You do like. Okay. Huh. Where's
Yeah, absolutely.
Okay. All right. So what we just did was we took this differential equation, and I'm going to show you by hand. We took this differential equation and we assumed that the solution was in this form, an times sine of mx, and we plugged it back in. I'm going to show you that, and did some coding to actually match that. So the cool thing is you can, a lot of the times, assume any type of solution in terms of an and sine and cosine, and you can get back to the differential equation and actually get it to work. Well, how do you do that? Well, let me show you these steps. And we'll go back to the programming as we do it. Okay, so my boundary conditions were 0. And when x is pi, so 3.14, 1519, that's 0. We're assuming that the solution is this form. And what we need to do is we need to take the derivative t of 0. X is 0. So if we take the derivative of an sine of nx, it's just n times an cosine of nx. Nothing too dramatic right now, right? Now we're going to take the second derivative. Minus n squared an sine of nx. Now we plug back in. An sine of nx equals x squared, and we have this. So we need to understand how we do this, how we program the next step where we do the linear and quadratic cubic approximations, okay? So we have this right now. We plugged it in. What we need to do is, and this is a standard application, like a rule, is we need to multiply and integrate. So this is a standard method if you are going to apply basically FEM from here on out. If you have a differential equation, basically you assume a linear, quadratic, cubic, or sine or cosine like we have. We find the derivatives, we plug them back into the differential equation. Once you have that, the next step is basically you're gonna multiply by sine of mx and integrate from 0 to pi. Okay, that's the standard policy of this procedure. So what we have is this: 0 to pi sine of mx parenthesis summation of big N little n negative n squared an sine of nx minus x squared dx. So you're trying, hopefully you now understand, okay, where the integration came from in our code. It's just a standard procedure when you're approximating these differential equations, is that's what we have to do, okay? And there's a lot of stuff to go behind why that is, but just kind of know that. What we need to do is we need to look at two terms. That term and that term. So term 1, term 2. And I'm going to break down the terms. So let's look at term 1. Bless you. Bless you. You all right?
Yeah.
What's that?
Why sine mx?
Because that's what we have. That's the standard procedure right here. Is we multiply by sine of mx and integrate. Okay, and what I'm going to do is I'm going to show you with numbers what happens to this term. Okay, so we're going to pick m is 1, and n will go from 1 to 5. So let's rewrite this to show you how this is actually written. So 0 to pi sine of x times. How many terms are going to be in the next section? What's big N? Or what's little n going from? 1 to 5. So there's going to be 5 terms in here. Okay? So let's write each term to show you how this is actually written out. I just brought that one down to the next line. And you're going to realize that FEM is actually a lot of math, a lot of properties. Like we've done a little bit of math right now, but you're going to see this Thursday and Tuesday it's crazy math, crazy stuff that you've probably never seen before. But I want to show you, so when you start doing more of this or in the workforce, you have an understanding of where some of this comes from. Now, there's some math properties that are pretty crazy. If you multiply sine of x times sine of x, anybody have any idea what that value is? If you don't know, put it in your command window right now. Throw it in the command window. This is what I would do if I had no idea. Like, okay, what is sine of x times sine of x? So pick something. Pick 2, 3, 4, doesn't matter for x. Tell me what the value is. That should look very familiar to you. I don't know, try it. What's 90 degrees in radians? Okay, do type pi divide by 2. What do you get? Look at that. Same thing. Should be. What?
If I do pi divided by 4. I don't know what you're talking about.
Pi divided by 2?
Sine 2 times sine 2. Pi divided by 2.
Oh, that's not the same thing. It should be the same thing.
Maybe 2 doesn't work.
What? You should get pi over 2.
Even when I look at pi.
Oh, sorry. That's not right. Should be the integral of 0 to pi. Yeah. Yeah. You can't do that right now very easily. But if we integrate these, you should get pi over 2. I think I have a code that we can write to show you that. What's that? Yeah, if you integrate that. Yep. Then if you integrate anything else, of like 3x or whatever, you get 0. Okay? Yeah. So, if we look here, see this term and that term right there? That term will give you pi over 2. What does the rest of this give you? 0. Okay? So this actually simplifies basically the pi over 2. Okay? And if you notice in our code, we have that pi over 2 for r, I think. Okay? But we'll go back to it. All right. Where's my next page here? So, what we can do now is that goes to pi over 2, which is actually, there's a negative in front, so negative pi over 2, whoops, times m squared times am. This is actually now term 1. Then minus 0 to pi of sine of mx times x squared, and this is all times dx. This is terms 2. And what we did here is we assume that n is equal to m and an is equal to am. And it doesn't matter, because if we take the above value up here, if I look at the underlined red here that I'm going to show you, doesn't matter if it's x and x or 2x and 2x. When you integrate that, you always get pi over 2. So m is equal to n. So this is term 1, that's term 2. So if I go back up to here, where I defined them, so term 1 and term 2, that first term actually simplifies to pi over 2 times this an value, which is some constant that we haven't figured out yet. Okay? Then term 2 is exactly what we had, which is here. All right? So, recap what I've done. We took this differential equation, way up here, zoom out just a tad, and we're assuming the approximation to a sine wave. All right? I'm going to show you in a little while, we're going to do a linear approximation or quadratic or cubic, doesn't matter. The rules are all the same. Basically, you take this, you plug it back in, you find the first derivative, you find the second, you plug it in, you end up getting this, and then you integrate by multiplying by sine of mx, and then you integrate from 0 to pi. Standard rules. Okay? We did that. We had 2 terms. The next step into these is to see if you can simplify things. And we can. The first term actually completely simplifies to negative pi over 2 m squared times am. We can find that. That's easy. Over on the right, it's just an integration. What you need to do is you need to solve for am. You get negative 2 over pi m squared. Integrate from 0 to pi. Sine of mx times x squared dx. Then the solution is the summation, we can do m, of this. So, when you multiply by the mx and you integrate, it does a couple things. The first thing is it helps you simplify one of the terms so it's a nice easy number that we can find. Okay? The second is because we need to actually figure out what this am value is to plug back into here. All right? So, now it becomes, how do you program this? So you need to do this. Okay, then you need to do that. And that's what we did in the program. So let's go back, see that a little more clearly to see if it makes sense. Any questions on the procedure? It's a little funky, a little different than you're probably used to. But these procedures are going to be used for future, and that's why I wanted to show you this first. So finish writing that, and I'm going to go back to the code, and we're going to talk about it. Okay, so I'm going to do that. And I'll spit that over here. Let's see here. Can I make this smaller? Yes. Okay. So the top is just, if you did that by hand, theoretically, that's what you'd get. Okay? So that's just differential equations. So when we look at lines 16 through 22, what are we doing in lines 16 through 22? We're integrating. What are we integrating from? 0 to pi. Okay? So line 19 is actually just this integration one time, right? Because m is, if we just picked m as 1, okay? But what we need to actually figure out is how many ends we're going. We're doing 10, right? So how many coefficients are there going to be? A1, A2, A3, all the way to A10. Okay, that's why I had it in a loop. So I'm finding A1 in this term here. What is, so line 20, I'm just evaluating that number. But then what is R? That's this term right here, right? Okay. That is -2 divided by pi times m squared. And how many of those values should I have? Should I have 10 of those values. Okay. Then what do I do on line 24 to 26? It's multiplied because guess what? That's what? It's A1, A2, A3. So go ahead and type right there on line 27, type return. R-E-T-U-R-N. Okay, and sorry for Kyle and Ryan that you can't get the word. But run the code, go to your command window, and then type AN. I'm hoping it should only give you 10 numbers. Are you trying to re-download it?
Like on to just like return on line.
Yeah, right there. That's return right there. And then run it, and then in your command window type AN. It should only be 10 numbers. Hi, do that. AN won't be undefined. Why would it be undefined? Because I don't have seats. So your command window type AN. How many? There's 10 coefficients. We just found 10 coefficients. That's what we needed, right? Because how many components of this are there? There's 10. Okay, so we need to have 10 of those. Okay, what happens if you change this to 100? How many are you going to get? You're going to get 100. What do you think would be better if you had lower numbers or higher numbers? Higher, okay, because basically you're making more coefficients, it increases it. All right, so let's keep moving down now. What is line 28 through 30? In mine, or it's the big G. All I'm doing is this term right now, right? So I've already found the coefficients. How many of these G, capital G values should there be? 10. Okay, so I just found capital G, I found 10 of those values. Then what did I do for line 32 to 34? I multiplied them together. Okay? Then what is line 36, that F? I'm adding them all up. Okay? That's that, and then that's basically that's what this is. We're adding them all up. Okay? Then I defined X, which is later on, and then we plot it. Okay? Questions? Pretty crazy, right? But I could tell you, this would be like a good practice in MATLAB, right? Do this with that. How would you program it? I hope you have a little bit more understanding of how you would program it now with for loops and integrations and stuff. Okay. All right. Let's take a 10-minute break. Okay, and I'll continue with some more notes to help you where we're going from this. Okay, so take a 10-minute break. I'm going to pause this. We won't do all of this, but we'll get a good chunk of it done.
It has tailgate. Look at it.
No. Okay, let's get back to this. So I'm going to go through what they call the weighted integral method. It's pretty long, but I want to show you because this is the fundamentals of FEM and ANSYS and Inventor. Everything that happens behind the scenes, I'm going to show you how it works. Okay. So that looked familiar, right?
Sure.
What is it? Sure, what's on the left? Nope, on the left. Conduction is convection. Okay, so this is the heat equation. We've done this. What is the first step they like to do in FEM that we've done 2 times in 2 homeworks? To differential equations.
Oh.
What's that? We did something to that. What did we do to it?
I can't remember what it's
Huh?
called. Yeah.
Someone said it maybe.
D something ties
Yeah, okay. Non-dimensionalized it.
Non-dimensionalized.
There we go. We ended up with this. Yes, so they non-dimensionalized it. So that's kind of the first step when you have a differential equation, is non-dimensionalize it. What does that do? It just makes it a little easier to look at, right? And we need 2 boundary conditions, right? 5/3, and I think we did the derivative. That x hat equals 1. 1 minus t hat. And I think you actually solved this one by hand. You didn't do the other one with the beam of the magnet, right? So, we have a differential equation. The rules state this. We're going to derive what they call the weighted integral form, which is you multiply by a function and you integrate. I hope that sounds familiar. Okay? So, remember when we had the one we just did with the sine wave? What did we do? We multiplied by a function, which we called sine of mx. And we integrated from 0 to pi. Well, it's the same process. You integrate by a function, you multiply by some function v, and it won't be today, it'll be Thursday when I show you what that function is. It could be linear, quadratic, cubic. And you integrate from 0 to 1. Why we're going from 0 to 1 is because everything's non-dimensionalized now. It goes from 0 to 1. Everything is from 0 to 1, okay? So it's the same process that we just talked about, and that's is where it's applied. Okay? What we're going to do is some more math to simplify this stuff, but we're going to pick the temperature for each element to be linear, quadratic, or cubic, and the same thing goes with V. So we will, just to give you a heads up, we're going to assume, you can write this down if you want, this will be on Thursday, that T hat is a function of a 1x hat plus a 2x hat squared plus a 3x hat cubed. And V is pretty much the same but different coefficients. And it goes back to when you did direct formulation, you had equations, direct equations for each element. Here, all we have is a beam or a fin. We have the differential equation that we need to solve. We need to multiply by a function, integrate. And then what we do is we pick. It could be linear, it could be quadratic, it could be cubic to the fourth, fifth, whatever, it doesn't matter. Okay? This is a very simple way of doing this. Because it's only 1D, only X. Okay? If you had a Y direction, you do the same exact stuff, but in these equations, you're going to have functions of X and Y. It could be linear, it could be quadratic, doesn't matter. Okay? So the next step that we need to do is basically try to simplify this differential equation and break it up into parts. Like we did with the sine of mx times the sine of nx, and we integrate, we got pi over 2. That's the next step that we need to do. Okay? So, let me break this up into terms. We have this first term, v d over dx hat, dt hat over dx hat, times dx hat, minus integration of 0 to 1 of nu t hat v dx hat equals integration 0 to 1 minus nu v dx hat. So 3 terms. Should be 3 terms. Una, dos, tres.
Well, I can't do this anymore.
I hope so far I'm not losing anybody, right? No? Okay, go way back up here.
Yeah.
First step you need to do is you take that differential equation and you do what? Non-dimensionalize. Okay. What if we take a step back? What is a differential equation? Where does it come from? How do we get a differential equation? Have any idea? The easiest thing is, okay, let me show you. Students in vibrations, it's just Joe and Dante, they know. If I have this, and this thing is, there's a mass on a spring and it's vibrating back and forth. If I pull this thing to the right, which way does the spring force want to go? Back this way, right? And that's Kx. If this thing is going to the right, it's going away from an equilibrium position, it's actually slowing down. So the inertia force is going back that way. And what's inertia force in physics? MA. Sum of the forces equals MA. That MA term is an inertia force. Okay? How can you rewrite A in terms of X? This is the second derivative. Okay? And guess what? What's that? Science, math, physics, it's everything. But what is this in math terms? Differential equation. Thank you. So what is a differential equation? All it is sum of the forces. It's just forces written in different form. That's it. Okay? So go back to this. Over to there is just, it could be forces, it could be moments, it could be energy too. Okay? You can think of heat transfers as energy. Okay? Written in a different form. So that's just all a differential equation is. And what is t a function of? Throwing a lot of stuff at you. Good review. T is a function of x. That's what defines a differential equation, is that you have a function instead of numbers. That's all. Okay, so we have a differential equation. We non-dimensionalized it. Then what did we do? We multiplied that differential equation by some function v, and we're going to integrate from 0 to 1. What is v, and what can we assume t to be? Well, for each element that we're going to break it up, we're going to assume it can be linear, quadratic, or cubic. I'm actually going to show you cubic. Okay? And I could probably give you, one of the homeworks I had last year was they had to do quadratic, which is actually easier. You just chop off a whole bunch of stuff. Okay? You're going to get a solution that's more accurate as you go higher up. Okay? The next step is to break it up into terms and look at each term. All of this stuff that I'm showing you is all behind the scenes in ANSYS or Invention. All of this happens. Okay? Okay, so let's do more math stuff. Let's do term 1 and then we'll stop for today. Okay? Because this one is pretty crazy. So let's look at term 1. Anybody guess what we have to do for a math rule? We have v, which is a function, times like derivatives, and it's like a second derivative kind of thing. We have to do integration by parts. I'm going to just go through this. Do you remember what integration by parts equation was? What was it? Almost. The way I have it is it's u v minus integration of v du. Okay, but these v's are not the v's that I have there. They're something else. Okay? So u is actually v in our case. Du is dv dx hat times dx hat. I'm going to do v2 is this. And therefore dv2 is what I wrote. And again, this is some math, some crazy stuff. As long as you kind of understand the process and where it's going, that's the key. And then we'll program it when we get the final answer. Okay, show you how to program. So we're going to do integration by parts. It's u, v minus integration of v du. In our terms, u is v. So du is just a derivative of v respect to x times dx. Okay, the derivative. And then v2 is just the actual derivative of t with respect to x. And then this last term is what we have. Okay, so let's now plug in term 1. And I'll do that in purple, and then we'll do the rest in orange. So we have, so it's u, which is v, times d, the derivative, from 0 to 1, minus the integration of v2 from 0 to 1 of d2 hat over dx hat times dv dx hat times dx hat. So if I do this in red and show you, this is the u term, this is the v2 term. This term right here is the what? V2 term. And this term is the du term. And all of that is evaluated from 0 to 1. That takes care of term 1. It wasn't too bad. So then we do what? Minus 0 to 1 and u t v times dx hat equals 0 to 1 and u times v times dx hat. Actually, that wasn't too bad, so I lied. A little bit more. Questions so far? Understanding the process, sort of? Sort of, Kyle? Okay, the next line I'm going to do is I rearranged and kind of factored like terms. So 0 to 1 negative, big bracket, the derivative Okay, so I just kind of did some factoring out on the left, and I rearranged one of the terms to the right side. All right, next line down is the negatives can go away. So we eliminate the negatives and factor out that term. So let me redo this in a different color. Let's do orange. 0 to 1. I think this is going to be the last where we stop. It's perfect. oops. This is evaluated, oops. Evaluated at 1, evaluated at 0. And I don't need this parenthesis here. There. Okay, so really, these last few steps was splitting things apart, doing some integration by parts, bringing them kind of back together. Over on the right, this right here are just boundary conditions. They're evaluated at 1 and evaluated at 0. Okay? So the key thing that I want to point out is, see everything on the left? You have t, hat, and you have v. That's called a bilinear function, because there's 2. On the right, you have just v here, this will actually be a number, and v here, and that'll actually be a number. So you only have v really over on the right, which is called a linear function. Okay? So typically what you'll see is v comma t equals L of v. So bilinear and linear on the right. Okay? That's how you have to process all of this, is to do that and then that. Okay? We on Thursday we have to do one more thing to keep going. Then we'll have a standard bilinear and linear function, and then we'll be able to program and do these things. Okay? So Thursday and Tuesday we'll probably just be in here just taking notes, writing code. So bring your computers. See if we can fix your computer on.
It works now.
It does work now. Okay, perfect. Okay, I do have those 2 computers. So Kai, if you can't get yours, we can use that. And then we do have that if they're not using that. So I figured kind of give you more of just like intense in-class work, but no homework. And next Thursday, probably what I'll do is I'll give you more answers to work on. Okay? All right. Okay. Thank you.